Okay, now we're going to be solving logarithmic equations. So we've been solving equations in exponential form, and sometimes we introduce logarithms, but here we're going to be given something with logarithms and have to solve it. Okay, we're going to skip the exploration and we're going to head to the next page here. So when attempting, no, that's not what I want. Here, solving logarithmic equation using the laws of logarithms. A logarithmic expression is defined only for positive values of the argument. When we solve a logarithmic equation, it is essential to verify that the solutions do not result in the logarithm of a negative number. Solutions that would result in the logarithm of a negative number are extraneous and are not valid solutions. Values obtained by solving logarithmic equations may be extraneous and must be verified. There are two verifications required when the solution is replaced in the original equation. All the arguments of the logarithms must be positive, and if the base is a variable, it too must be positive. So those are important checks, as we may get some solutions that aren't really solutions. So solve the following logarithmic equations. So the key to solving logarithmic equations is, in the first type, we're going to use our laws of logarithms until we have the log of a base equals the log of the same base. Because what happens now, we can say that if log base 10 of x squared equals log base 10 of 16, that tells us that x squared must equal 16. Well, that tells us that x is equal to positive or negative 4. Now, we need to check whether these are both solutions, so we need to verify. Well, the only place we have an x is here, so we just need to make sure when we put this value in, we're taking the logarithm of a positive number. Well, the log of negative 4 squared is equal to, the log of 16. We can calculate that. Same thing if we use positive 4 there. So the log of 16. So it's fine that our x is negative as long as when we substitute it into our equation, that logarithm has a positive argument. So two looks trickier. First, remember our goal is to have log of something equals log of something else. But in this case, we have a 2 in the way. Well, if we divide both sides by 2, now we just have a 1/2 over here, so that doesn't help us. So we want to use our logarithm laws. So to do that, we know we can rewrite this with the 2 as an exponent on the argument. So now we have this. So that gives us x squared equals 16, and x equals plus minus 4. Now when we go to verify, though, when we go into our left-hand side, if we look at 2 log of negative 4, now we have a problem, because now we have a negative argument here. So negative 4 is an extraneous solution. The only solution that works is positive 4. So even though after a step we could write these as identical, since they started out different, they don't have the exact same solutions. You could solve this by graphing as well. And if you graph the first one, so if you graphed y equals log of x squared minus the log of 16, you get this. Whereas here, if you graphed y equals 2 log x, log x minus the log of 16, you would only get this portion of it. So solving by graphing is always a good way to make sure if your solutions are extraneous. So when you're graphing, you will never get an extraneous solution. You'll see that this only has one x-intercept, and it will happen at 4. So it's always a good idea to solve by graphing afterwards to make sure you caught any extraneous solutions. The other method you could use is to consider the domain of the functions before starting. So if we look at the domain of y equals log of x squared, the domain is any real number, except x cannot be 0. We can't take a log of 0 because 10 to the power of nothing will give us 0. So we can't have an input of 0. For the domain of 2 log x, well, now our domain is x is greater than 0. Okay, of course these get trickier. So solve for the following. Log base 4 of x plus 1 minus log base 4 of 2x minus 3 equals log base 4 of 8. So remember, our goal here is going to be to write a logarithm on both sides in the same base so that we can just look at the arguments. Well, these two logs have the same base. They are being subtracted. So that means I can change this to division. Notice how I don't divide the logarithms. I write it as a single logarithm and divide the arguments. So now, since I have log base 4 on both sides, this becomes x plus 1 over 2x minus 3. Whoops, I don't need the logarithm over here anymore. I have 8. So this only works, just like exponential equations, if those bases are the same. So now I need to solve for x. So I can multiply both sides by 2x minus 3. Bring the x's to one side, the numbers to the other. And we get x equals 25 over 15 equals x. Oops, 15. Or 5 over 3 equals x. Now you should verify it to make sure it works and it's not going to give you a negative number. So the shortcut would be to say, well, what is the possibility to give me a negative number? Only this one, because we're subtracting something, right? 5/3 plus 1 will be positive. Check that 2x minus 3 remains positive, and it does. And then you always want to, it's always a good idea to substitute in and check to make sure you get the same answer you do on the right-hand side. Alternatively, you could graph this and make sure that this is a solution. So x equals 5/3. Okay, B, we have log of 6. Log base 6 of x plus 4 equals 1 minus log base 6 of x plus 1. So this one's a little bit different. One way we can do this is first to bring our logarithms together. So you notice how 1 is not in a logarithm here, so we can't say let's rewrite this using logarithms of the same base. We can bring our logarithms together. So log base 6 of x plus 4 plus log base 6 of x plus 3 equals 1. Now we can combine these two logarithms together. They're being added, so to bring them into one logarithm, I'm going to have x plus 4 times x plus 3 equals 1. And now, I don't have a logarithm over here, but what I can do is change to exponential form. So remember I said in this unit, there's a few things. You always, whenever you're stuck, try and combine two logarithms into one, or separate one logarithm into two using your log laws, or change base. So I got stuck once I was here. So I can, sorry, not change base, change form. So here I changed form. Well, now I can multiply out this side here, x squared plus 7x plus 12. Subtract 6 from both sides. And I can factor. This factors to be, whoops, this should be 6 now. So two numbers that multiply to 6 and add to 1 or add to 7 are 6 and 1. So I get values -6 and -1. We want to verify. Well, it should be pretty quick to see that this is an extraneous solution. If you substitute -6 in this logarithm and this logarithm, we'll have a negative argument, which is a problem. So that cannot be a solution. -1, however, works because we still have positive arguments. And again, you could solve by graphing to check. Example 3. 2 log 3 of x minus log 3 of x plus 3 minus 3 equals 0, and we're solving this to 2 decimal places. So we have some logarithms on this side, so let's start playing with our log laws. One thing we can do right away is bring up that 2. Now I see I'm subtracting these two logarithms, so I can bring them together using division. Okay, now I have this. Well, now I'm going to bring that 3 to the other side. So now again, I'm getting it to a form where I can change form. So now I can say 3 cubed must be equal to x squared over x plus 3. Now to solve this, I have 9 times x plus 3 equals x squared, which gives me x squared minus 9x minus 27. Now it wants to the nearest, or to 2 decimal places. So now what happens is we go to the quadratic formula. This cannot be factored, so we go to the quadratic formula. And we get 2 values. We get 29.72. And we get negative 2.72. Well, you always want to check, are these both valid solutions? But right here I have log base 3 of x, so I cannot have a negative number, so x is simply 29.72. So basically your goals for these relatively simple logarithmic equations are to either have log base something equals log base something on the other side, and then you can ignore the logs, or get it to the form where you have a logarithm like this and a number on the other side so that you can change to exponential form. But of course it does get more complicated, so this is a bit of a longer video here because these get quite a bit harder. Solve the equation log base 2 of log base x of 3x plus 4 equals 1 by twice converting to exponential form. So the first time converting to exponential form, remember you can lock this together and just think of it as the input. So I'm just working with the outside logarithm first. It had base 2, so I can have 2 to the power of 1 equals this entire input. And now I can change again to exponential form. Now I'm going to have x to the power of 2 equals 3x plus 4. Bring everything over, x squared minus 3x minus 4 equals 0. This can be factored to be x minus 4, x plus 1 equals 0. So the two solutions I get there are negative 1 and 4. So here I need to eliminate this solution, but for a slightly different reason. So here I need to eliminate the solution because I have a logarithm with base x and I cannot have a negative base in my logarithm. So my only solution here is x equals 4. Okay, last example here. Solve the equation log x squared minus 3 log x equals 10 by using the logarithm laws. So one way to do this here, you have a couple choices. You could bring this 3 up, or you could bring the 2 down and see what happens. So this time I'm going to bring the 2 down to see what happens. Either way it would work, and there's lots of different ways of doing these questions. So now I have 2 log x minus 3 log x. Well, since these logarithms are the same base, and they're both log x, both have the same argument, I can combine these. These are like terms, so I can now say negative 1 log x equals 10. Dividing both sides by negative 1, I get log x equals negative 10. Well, now I got a form I can work with because I have a logarithm and a constant, so I can change to exponential form. My base is 10. Remember, if no base is written, it's a base of 10. And if I want to write this with a positive exponent, I could also write it like this. So substituting in, you see that this is positive, so I have no problem inserting that into either one of those logarithms. Now, why would the same process work for this next question? So this question looks very similar. The difference is our power law only works if the exponent is on the argument only. And here our exponent is on the whole logarithmic expression, not just the argument of the logarithm. So we need to come up with a different method to solve this. So these are the hardest ones. Solve the equation in B using the following steps. Replace log x by a new variable a. So I'm going to have a squared minus 3a equals 10. So of course you could pick any variable. They picked a. Now I'm going to solve this for a. So this is a minus 5, a plus 2. So a equals 5 and negative 2. Okay, well, I can't forget what a was. A was log x. So this really tells me that log x equals 5 and log x equals negative 2. Changing to exponential form, that means 1x is equal to 10 to the 5. And the other x is equal to 10 to the negative 2, or 1 over 100. So now we could verify those, but they're both positive, so we're not going to run into problems. This is 1 over 100, and 10 to the 5 is 100,000. So those are our two solutions. Okay, a student is solving the logarithmic equation log x squared minus log x cubed equals 0. Her work is shown. So have a look at this work, and you'll see that she went wrong somewhere. So where she went wrong is recognizing the difference between these two expressions. She treated it as if it said minus log x cubed. But in this case, the exponent was on just the argument. So for the second expression here, we could use our log laws. So what she should have had was a squared minus, well, we could write this as 3 log x, but we're replacing log x with a. So she could come up with this. Factor on this side, and I would get a equals 0 and 3. Now remember, you need to go back to your expression. A was the log of x. So our x values here, well, 10 to the power of 0 is 1. 10 cubed is 1,000. So our solutions are 1 and 1,000. So we could go back in and check, and that's where she found her answers to be wrong. If you'd substitute those values in or solve by graphing, you'd find that 10 was not a solution. So something went wrong.